there's this big project that's been running for the past few years, the Good Judgment Project, where they get people to make predictions about geopolitical things in the world, and they're really trying to assess actually what makes people good predictors and whether you can do better by combining people than individuals, and how best to do that. And the answer is you can find people who are do noticeably better than the average. This doesn't always line up with the kind of most credentialed experts on a field, but aligns a bit with not being particularly dogmatic about anything and being open to lots of different perspectives, and using lots of different weak sources of information and trying to aggregate these. In a sense, they might be doing something a little bit like this wisdom of the clouds thing within their own judgment. But also then there are ways that you can try and organize people into groups and produce systems for getting group judgments out, which are in some sense a consensus, and you allow feedback between these, which can beat individuals. So there have been some attempts to do this going back several decades. The Delphine method is one thing for trying to get something like a consensus out of a group of experts, which beats just asking an individual. And also, it is known that people can be sometimes bad at understanding really what probabilities mean. Phrasing the questions differently can produce different answers from people, even if they're logically equivalent. And you can work out, okay, which are actually the best ones of these to use. And there are other biases which, where aware, affect people and may distort their answers. The better you understand these, the more you can attempt to correct for it and end up with good answers. Anyway, I think this is extremely important. I personally don't know that much about it, which is why I've gone over it moderately quickly here. But it seems like, as a society, it is important that we work out more about how actually this ought to be done, and then also go and work out how we can set up institutions to make sure that it is done more systematically and reliably for important questions. So another method which you can use for trying to get estimates out of a lot of people and then pull them is the idea of prediction markets. Quick show of hands, who's heard of prediction markets before? Half the people, okay. So the idea is a market in the same sense as the stock market. The stock market, you buy stocks and then they rise or fall according to how much other people think that the companies in question are worth, and then you sell them later. And they get some ultimate value because in the end the company will make money or not, and it can sell dividends to stockholders. Prediction markets, you try and set up a market in predictions. Like we could have a market in will it rain on Monday? And we could, so it's a bit like just betting about the future, but you set it up in a market format which makes it easier to facilitate trade between people. And so I could make a market by issuing a bond and saying this will pay. I will pay out £1 if it rains on Monday. How much will you give me for this? And somebody could say, okay, I'll give you 34p for it. The amounts of money here are probably small enough that they're implicitly showing it that they think there's about a 34% chance that it will rain on Monday. And then they bought this, and then later we get a bit more information. The Met Office updates the forecast, and somebody else thinks, and it looks like it's more likely to rain than this. Now they don't need to hold on to that thing until it's actually resolved and does rain or not. They can sell it. And if it now looks like it's more likely to rain, then they can sell it for more money. Maybe they could sell it for 50p and make a profit. And so you can trade on these markets just like you can trade on things like stock markets. So fine, some people like trading on markets. This looks like it might be good for traders. what's the other benefit? Well, something we're doing from this is, if there's a whole load of trading on this, then you'll end up with something like at any time there'll be a price for a thing, because you're not going to have in a big, fairly efficient market, some of the bonds that will pay out £1 if it rains on Monday selling for 20 pence, while some others sell for 70 pence. Because if it looks like there are lots selling for 20 pence, nobody's going to be willing to pay 70 pence for one of these things. So what that means is that there's kind of a price for the thing, and if it looks like they're trading at about 20 pence, we can read that off and say this looks like there's some aggregate judgment from all the people involved in the market, or who could be involved in the market, if they thought, actually, I know more about the rain, there's money I can make here, that the chance of rain is about 20%. So what that does is it sets up a way of aggregating judgments of lots of different people, which doesn't need you entirely to go and identify the right experts in advance, and is somewhat robust, because if the answers are systematically wrong and there's ways we could identify that, some people probably will identify that and then they'll make money out of it. And then in the future they'll have more money, and so their opinion will get weighted a bit more heavily on this. So there's these are not widely adopted, but there have been some cases where they've been used in the world, and there's evidence that actually they often do better than individuals making judgments. So this seems like it may be a fairly good way to try and get some social judgments about probabilities. There are some issues that you need to resolve if you want to use them. One is that it's not always clear how to set them up. In general, they seem easier to run for things that are coming a short time in the future. If we're running this for something that we won't find out for 20 years, then maybe I have to have my money locked up for 20 years, prepared to pay out if it rains in 20 years, if that's what we were betting on. Also, some things, now, people can still trade on it, even if it's not going to pay out for a long time in the future, as long as they expect that eventually it will pay out, because even if it were not coming for 100 years, presumably there'd be people in 90 years who would be willing to take a 10-year bet and pay for that, and so they'll pay something for it. But then, because predictably there'll be people in 90 years, the people in 80 years will pay something for it, and so forth. And so, in theory, these prices should work right the way back to the present. There's some friction there which can slow this down. Also, if we said something like, okay, let's have a market on what is the chance that we're all wiped out by a pandemic, who is going to bet that we're going to be wiped out by a pandemic? Because if we are, then there's nobody left to collect and actually make money. So for some of these very big questions, it's hard to formulate markets. For some other things, it may just be hard enough to set it up in a precise enough way. We want to have a very unambiguous statement that we're betting on in order to produce a crisp market. There's also a question about actually how can you encourage participation. If there's not enough money in these things, then they're not all that accurate. And as they become larger and more fluid, there's basically more mental energy that people are investing into trying to work out how to get an edge there and try to work out actually what the probabilities ought to be, and that means that the probabilities are more accurate. When they're quite small, the probabilities can be quite inaccurate. And then there's sometimes some problem with encouraging moral hazard, and increasing moral hazard, encouraging people to take actions that actually we don't want to encourage them to take. So we could have a prediction market on whether the Prime Minister of the UK will be assassinated in the next year, but somebody might go, oh, well, I'm going to bet a lot on that he will be assassinated, and then I'm going to go and try and make sure that happens. And so we can't treat these as entirely exogenous. if the amounts of money are small enough, it doesn't change the incentives much, but that the amounts of money being small enough is exactly the case where we just don't think that they're all that accurate anyway. It could also be that people pay attention to what the numbers are in the market, and so if people are going to say, okay, we're going to use these prediction markets as a form of social institution for working out the likelihoods of different things, and we're going to make decisions based on what the probabilities the decision markets say are going to happen, then people might actually start saying, well, I'm going to invest in the decision market to make the probability look like this so that different decisions happen. There's some evidence that this may have happened in the past. There was prediction markets on the last US presidential election, and it looked like there was an effort to, in the markets which were mostly open to US people, an effort to make it look like Obama was less certain to win than he actually was, relative to markets that were mostly open to European people. So there was actually, like, you might think, well, kind of theory says this shouldn't be able to persist. Some people should go in and arbitrage these, and then the percentages should line up. So it was a little hard to do that in mass. I mean, actually, I know people who did arbitrage it. I did. I bet a few £1,000s on Obama in the US market and a few £1,000s on Romney in the UK market, so that I was guaranteed to end up with about £500 profit either way. And I know of a few other people who did this. So we shouldn't be entirely... prediction markets look like they have quite a lot of potential value, but we maybe can't trust them too much. Okay, that was all ways of getting good estimates out of people from what people already do and working like how to use them. This seems like a pretty good approach. But there's some reason to try and ask the more fundamental questions. And this is of like, well, okay, but how can we, without just going and asking people, like in principle, how can we estimate these things as well? Why is that useful? One, because it, how do people, like individuals' judgments improve? One of them is by going and understanding these concrete models and building up better internal pictures of how the system we're looking at works. Another is that having dialogues about how the different likelihoods of things is much greatly facilitated by having concrete things that we're discussing and that you can pull around and push one way or the other. So there are reasons, even if we think that ultimately decisions in the world often want to be made with the first, after using a lot of the first kind of method, to do this investigation into, okay, but in principle, where do these things come from earlier as well? And feeds in kind of earlier in the entire process. This is, so Andrew Critch talked a couple of weeks ago about artificial intelligence, and understanding where beliefs about probabilities ought to come from also looks like it may be a relevant question for artificial intelligence, because they will often want to be acting as though they have beliefs about things, and we might like to understand better where those beliefs ought to be, about probabilities ought to be coming from. So the basic approach here is this kind of Bayesian idea that you start with some prior probabilities about how likely you think things are, then you go and look at some evidence, and then you update the priors in light of the evidence according to how likely the things were to have produced that evidence, and get posterior probability distributions. There are a lot of nice theoretical things to be said about this. There are a couple of problems that it produces. One is that it's not always clear where to get a prior from. And so it's kind of, you might think, well, it's just pushed a lot of this problem off into how do you get a nice prior. Second is that actually it can be a lot of work to work that all out properly, and we only have so much kind of cognitive capacity for estimating things. Computers we build only have so much computing power. Doing this all properly when there's very large amounts of evidence can get computationally infeasible. And so it's worth having an idea of what are good but faster heuristics that also produce good behavior. But let's look a little bit at kinds of ways that you can feed priors into this. One thing is, so a classic example of trying to reason sort of with a prior implicit from evidence is Laplace's law of succession. So he was talking about originally I think talking about like probability the sun comes up. And this is not a great example to use for this because this is most applicable when we've got a phenomenon that we've observed in the world and we've got some kind of historical record we can look at, but actually we understand very little about it apart from that historical record. So we just want to say, okay, given our ignorance here, what should we think? So maybe we know a coin may be biased, but we don't know what the bias is, and we flip it 100 times and it lands heads 80 of those times. Now, what should our best estimate be for the likelihood that if we flip it again, it will land heads? One thing is to just like take that historical record and say, well, it looks like it should be 80%. But now consider the case where you flipped it 100 times and they were all heads. Should we think it's absolutely certain to land heads if we flip it again? I think probably not. And this becomes more obvious if you kind of reduce the example to, okay, suppose we flipped it twice and it landed heads both times. Should we think it's 100% likely to come up heads if we flip it again? I think like basically everybody would think not in this case. But there are some systematic ways of trying to get a number out without from that, even when you've only seen one kind of case. So I think the like most reasonable rule here is if you've seen H heads and T tails, then estimate of the probability of heads should be two H plus 1 over 2 over 2H plus 1 plus 2T plus 1. And this, there's a load of statistics which is lying behind this. Basically, this is relying on it's Bayesian updating given a particular beta distribution as your prior. And this is the Jeffreys, this corresponds to the Jeffreys prior. I'm going to not say too much more about this. I'm happy to talk more about it. And there's also, there's a lot about this stuff, and you should feel free to ask them that.
Uh-oh.
So another thing you could think, and this is relating to some work I've done, is that sometimes it seems like we don't even need to know that much details of the prior in order to reach some qualitative conclusions. So in some cases, if we're trying to estimate a variable and we think we've got really very little idea what this variable is, then one thing we could say is, look, at least our prior, it's hard to like specify exactly, but our prior ought to be spread somewhat smoothly over several orders of magnitude. And so if you think this is a, I should have thought of an example to use here. If this is a log scale, of something. What are we extremely unsure about? We can make this a much more spread out log scale. We're extremely unsure, this is something Anders was talking about last time, what the probability of abiogenesis is, of life rising out of nothing. How frequently does this happen? It seems like this is a combinatorial question, but there's just like so much that it could do. So it could be anywhere between maybe actually this is extremely likely, and when you have a planet with the right roughly the right circumstances, then the rate is going to be something like 1 times per year per planet, assuming that it has about the right temperature and about the amount of water and so forth. But then maybe it's actually 10 to the minus 5 or 10 to the minus 10 or 10 to the minus. So it's going to, and even in fact, way lower than this or noticeably higher than this seem plausible. So our distribution is probably going to look sort of like this. And at least as a prior distribution. And then maybe, in fact, maybe it goes as a prior before we observe that like we don't just do this all the time in test tubes. It might go up way over this way. And then when you start trying to reason about this in the world, you can actually think that a lot of the impacts come from, even if we think that there's a significant chance it's extremely low, much of the impact comes from a range where it's moderate. This was not, yeah. This is why I should cut my examples in advance. I haven't traced through exactly how that comes to a conclusion. I'm going to move on because I've left myself too many different things I want to say. So I'm going to talk briefly about the Solomonov fire. This is an attempt to be actually a kind of comprehensive and systematic way of producing prior probabilities for everything. And so this is in the field is algorithmic probability theory, and relates to algorithmic information theory. And the idea is we'll use a simplicity bias. We'll say that as a prior, there's possibly, we can't just assume that everything is equally likely, because there are infinitely many different possible things that the world could look like. We just know that there are lots of, we can write down longer and longer descriptions, all of which are different. So there's an infinity of possible things there. So there's no way of actually having a probability on each of those in a way that they work as probabilities and add up to a finite number, unless most of them are 0. But what you can do is you can do it if the probabilities are shrinking fast enough that you have an infinite sum with, you're summing infinitely many things with a finite sum. If its probabilities would like it to be 1. And the idea is we'll have a simplicity bias. We expect things to be more likely if we can describe them succinctly. There's a lot of technical details of how this is implemented. Tends to be done looking at, assuming that the worlds that we're looking at are ones which are describable in a kind of computational manner, and maybe actually we have hypothesized a Turing machine, kind of theoretical computer, which could be generating lots of different things, and we assume that they're more likely if they're generated by short programs than by long programs. This may look a little bit arbitrary, but it has actually some really quite nice theoretical properties, which I do not, I'm not going to try and get into justifying properly, which are kind of dominance. It says that even if the real world goes and whatever the real world is, assuming it's drawn from the distribution of things that are anywhere in this, then we will eventually actually work out that that's the real world, given enough evidence, and our probability of that will go up very high. And that we won't take too long to get that. The kind of total number of errors we might make on the way won't be too high. So there's some reason to go for things like that. It's also there are also some complications associated with that, because the way that you assign those initial probabilities depends on the Turing machine that you fed in at the beginning. But I think in the interest of time, I should not spend too much time. I should just move off this. Because there's two more things I want to mention before we get to discussion here. So first is model uncertainty. And this is, we started out talking about like implicit judgments that people are making about probabilities, and then we've gone a bit into I haven't gone as much as I ought to have done into like one way that you try to get ideas of probabilities of things is to build explicit models about them and try to understand what those models telling you and get the model to, as far as possible, line up with reality. And this is very valuable and has historically done very well and enabled us to get a lot more probabilities and understand systems better than we did without this. Right, there's this point that the models often contain explicit uncertainty, like our model might involve a coin, which says that it has the 50% chance of coming up. That's different from our uncertainty about the model. It can be important to keep these apart, and in some cases, the uncertainty about the model starts to become the really dominant factor in our decision making. So this is a paper Anders was an author on a few years ago, Probing the Improbable, has a great description of how this can actually come out in practice, where if you're looking at situations where there are some low probability events according to your model, and you don't and they're extremely low probability according to your model, then your all things considered judgment about them probably assigns most of the probability not to the scenario, not to the case that the model is correct and we were just extremely lucky or unlucky to get into this low probability event, but to the case where the model was wrong as a description of the world, and it was flawed in a particular way. And this is something which comes up for real-world decision-making. It seems like the thing with subprime mortgages was significantly because people were not taking into account out-of-model uncertainty, like all this between-model uncertainty enough. They were saying, well, it's extremely unlikely that all of these mortgages would default at the same time. And indeed, they had a model which said it was extremely, extremely unlikely. And indeed, it was not the case that their model sort of, it just appears now, everyone thinks, well, yeah, the model was right, we were really unlucky there, but that the model governed things in one domain, and then we got a qualitatively different type of behavior. And the subjective estimates that we would move out of the domain where that model seemed to apply ought to have been much higher than they were. Maybe they just weren't being built. So that's worth being aware of. And I'll talk a little bit then about Pascal's mugging before we wrap up. Who's heard of Pascal's mugging before? So a little under half. This is a thought experiment. I am, say I'm out for a walk and somebody comes up to me and says, I'm going to mug you. I left my knife at home, but give me your wallet, or else I'm gonna track you down later and attack you with my knife. Okay, I might think, well, look, probably they're not going to do this. So if they had a knife there, I'd be like, okay, I'm just going to give you my wallet. In this case, I'm like, probably they're not going to do this, but is the probability low enough? Like, being attacked with a knife would be pretty bad. Maybe I just want to guard against that and give them the wallet. But maybe I think the probability is low enough that they won't actually do this. And I say, no. And they say, okay then, I'm not just going to track you down later. I am going to track down all of your friends and family and everybody you've ever cared about and torture them horribly. And presumably, I think the probability of this is a lot lower than the probability of the first thing. But it also sounds much worse. And there's a question about whether the probability is getting smaller faster than the outcome that they're describing as worse. And they might say, I might still think it's not enough, but they might say, look, actually, I have extremely large powers, and I am simulating untold trillions of worlds. And if you don't give me your wallet, I'm going to torture these trillions upon trillions upon trillions of people, and you'll be responsible. And there's an issue here that maybe, like, how should my probability, you know, it's far less likely that they're actually able to do this than that they're able to track down all the people I cared about. But should I assign it 0 probability? Because it sounds extremely bad if they could actually do it. And they can just keep on inflating this number of like people that they might be able to access. And should my probability be dropping fast enough in all cases? So that's the rough setup of Pascal's mugging. It's in analogy with Pascal's wager. Pascal thought maybe it was worth believing in God because even if there was only a small probability that God actually existed, you could get infinite payoff that way. And this situation is sort of similar, but we're looking at things which don't have an infinite payoff. They just have a very large payoff. You could also, maybe it's offering you many, many years in heaven, or you know, a fantastic environment instead of torturing people. It doesn't need to be all of that in there. And to be clear, from this thought experiment, I don't know of anybody who thinks, yes, you should give the mugger your wallet. But the challenge is to explain why you shouldn't give the mugger your wallet. And okay, why do we care? Because like this is not a situation. If everybody agrees that you shouldn't do this thing, it doesn't look like it's all that important to investigate why it is that you shouldn't. But maybe understanding the reasons could actually affect some of our other decisions. It could affect how much we pay attention to other things which seem to have an extremely large payoff, or a small probability of an extremely large payoff. In particular, maybe it could affect this argument that we were presenting earlier in the term, that it's extremely important to work to reduce the chance of human extinction, because that's a case where the payoff, ensuring the continued survival of the species, looks extremely large. The probability that anyone can do to actually to affect this end up making a difference is extremely small. How could, like, is this just a better dressed up version of the same argument the mugger is making and actually has the same flaw? It could also be this one I mentioned earlier, the general how to deal with unknowns, big unknowns, being something that's relevant if you're building an artificial intelligence. This one looks like it might definitely be relevant, because if you're building something which is going to go and make decisions in the world, you would like it not to end up handing its wallet over to the mugger when that happens, because then it might end up doing something extremely unpredictable. But you perhaps also want to make sure that it does end up going after things that you think it ought to go after. You don't want to, in trying to rule that case out, also eliminate from it the possibility of pursuing a lot of valuable activity. So there are a number of possible ways to try and resolve this. I've listed them in the section 6.3, but I think I shall not go into them now because it's actually a little more technical. But you could see people have proposed a number of solutions for this. None of them so far look entirely satisfactory. So it's still a bit of an open question about how this ought to be resolved, how people ought to act in these situations, and it looks like it's an important one. Okay, so I'll stop there, and there's biscuits, fruit, water, and maybe we can have some discussion. And then next week is the final seminar in the series where I'll talk about differential progress and this idea that maybe it's particularly important to sequence the kind of progress that we're making as a society in terms of for affecting the longer term trajectory. And information hazards, recognizing normally we think more information and knowing more things is good, trying to work out when that dynamic doesn't hold, how to recognize that and what to do about it. Thanks everyone as well for coming along this term. It's been a great experiment running these. I've been pleased to see so many engaged people and have good conversations afterwards. Yeah, it's possible we will end up doing something similar, going into a deeper dive on one of these topics in a future term.